Hi, this is Coach Cedric, and today I'm going to show you how to solve this math contest problem. This is a number theory problem from University of Waterloo's Cayley math contest, which is aimed at Ontario grade 10 students. This is question number 20 from year 2015, which reads that, given n is an integer, for how many integer values n will this expression, 72 times 3 over 2 to the power of n, produce an integer result? And let's just plug in some examples. For example, when n is equal to 1, the basic case, we see that 72 times 3 over 2 to the power of 1, which is just 3 over 2, the result is actually an integer. When n is equal to 0, for example, we know that anything to the power of 0 is actually 1, so therefore 72 times 1 is also an integer. Right? But when n is equal to, for example, say -5, you see that 72 times 3 over 2 to the power of -5 does not produce an integer, right? This is a divisibility problem. In order to solve this problem, we need some background knowledge on this divisibility and prime factorization. Feel free to skip this part if you already know this. When we talk about divisibility, it is important to remember that it's relevant to integers only. For example, let's take an integer, say 36, and I divide it by another integer, say 2, and the result is 18. I see that 36 is divisible by 2 because the result 18 is also an integer. Or I can say that 2 divides 36. Remember, it doesn't make sense to say, for example, 3.6 divided by 0.2, although the result is also 18, but we have decimals on this side, right? So divisibility is interested in problems such as, given an integer such as 36, what numbers can divide it? Well, if I want to talk about divisibility, we have to talk about a related concept called prime factorization, right? First, let's talk about factorization. Factorization means that I take any integer, I want to rewrite it as products of integer factors. For example, take 36, the most easy factorization is, the easy factor is 1 times 36, right? Or you can say 4 times 9, right? Prime factorization requires that when I factorize the integer, I also want to make sure that all the factors here are prime, right? So for example, as you can see, these two factorizations of 36, neither of them, right, is a prime factorization because, right, we need to make sure that every factor is a prime. So 9 is composite, 4 is also composite, therefore it's not a factorization. Or let's say you have 2 times 18, right? Even though 2 is prime, 18 is not prime, so therefore 2 times 18 is also not a prime factorization. Well, what is the prime factorization of 36 then? According to the fundamental theorem of arithmetics, there is only one and a unique factorization of 36, which is 2 to the power of 2 times 3 to the power of 2. How do we get this? Well, let's take 36 and let's start dividing it by prime numbers. And the first prime number that I can think of is probably 2. It's the smallest prime number, right? And 36 divided by 2, you're left with 18. Divide by 2 again, you're left with 9. Divide by 3 again, you're left with 3, right? So as you can see, right, 36 has 2 factors of 2 and 2 factors of 3, right? Okay. As an exercise, let's see how that's how you prime factorize 24, right? If you get the concept correctly, you should get this prime factorization, right? 6, and you're left with 2, 3. So therefore, 24 can be rewritten as 2 to the power of 3 times 3 to the power of 1. So you have 1 factor of 3 and 3 factors of 2 for 24. Now let's tie this back to divisibility, right? For an integer a to be divisible by integer b, we need to make sure that a's prime factorization contains all of the prime factors in b's prime factorization. What does that mean? Let's take an example of 36 divided by 24, right? The first step we do is to both is to prime factorize both the top and bottom, right? Now I know from previous exercise, 36 is 2 to the power of 2 times 3 to the power of 2. Whereas prime factorization of 24 is 2 to the power of 3 times 3 to the power of 1. We can see that 24's prime factorization contains one factor of 3. And the one factor of 3 can be accommodated inside 36's two factors of 3. So the 3 part is taken care of, right? So the 3 part has no problem. Now take a look at the 2 part, right? 24 has 3 factors of 2, whereas 36 has only 2 factors of 2. Therefore, there's not enough 2's in 36 to divide the 2's in 24. Therefore, I know that 36 divided by 24, the result is actually not an integer, right? But let's change the numbers a bit. Say let's say I change it to 360. Will 360 be divisible by 24? Well, let's use the same method to check, right? If you did the if you're familiar with the concept of prime factorization, you'll see that the prime factorization of 36 is actually 2 to the power of 3 times 3 to the power of 2 times 5 to the power of 1. Right? Whereas the prime factorization of 24 doesn't change; it's still 2 to the power of 3 times 3 to the power of 1. Now compare the factors side by side. So you see it has only one factor of 3, which can be accommodated by the 2 factors 3 inside 360. It has 3 factors of 2, and this time your 360 also has enough 2's to accommodate all 3 factors of 2 down here. And the 360 also has one factor of 5, but this is just there for cosmetic purposes because 24 doesn't have any factor of 5. Therefore, I know that this division is actually 360 is divisible by 24. Now, armed with these technical knowledge, I encourage you to try the question on your own. Now, let's take a look at this problem. So we recognize that it's a divisibility problem. It's probably very helpful if we rearrange it as a huge division, right? Remember, when n is non-negative, right? By the distributive law of the exponents, we can rewrite this as 3 to the power of n divided by 2 to the power of n. Another thing to do when you're dealing with the divisibility problem is to immediately prime factorize any number of integers. In this case, 72 can be prime factorized. And if you do it properly, this should give you 2 to the power of 3 times 3 to the power of 2. Right? And I want this result to be an integer. Right? Okay, cool. According to the law of divisibility, right, we need to make sure, if we want the result to be integer, we want to make sure that all the factors of 2 here can be accommodated by the top, right? So in the top, I only see one place that can produce 2, and according to the top, you can accommodate at most 3 2's, right? So therefore, any power of 2 should be bounded by 3. Therefore, in order for this expression to solve to an integer, n has to be less than or equal to 3. Right? So are we done? No. We'll only consider the case when n is non-negative. Now let's consider a case when n goes below 0. When n is below 0, right? Remember, when an exponent dips below 0, your fraction flips. Right? In order to express that, let's assume that there's some positive integer k such that negative k is equal to n. Right? So for example, when n is equal to -1, your k will become 1, right? Such that you'll be negated to give you -1. So remember, when you're dealing with a negative exponent, you can flip it. So 3 goes to the bottom, 2 goes to the top, and replace the negative exponent with a positive one called k. So 2 to the power of k times 3 to the power of k. Right? And the 72 doesn't change. Right? 72, we still rewrite it as a prime factorization, which should give us 2 to the power of 3 times 3 to the power of 2. And I want this expression to solve to an integer. Right? So according to the divisibility rules, I need to accommodate any power of 3 on the top, right? And the top can accommodate at most 2 3's. So therefore, k should be bounded by 2, which means that n should be greater than equal to -2. You see that? Right? So therefore, n can take on the maximum value of +3 and the lowest value of -2. So therefore, in total, at the end, n can take on values from -2, right? -1, 0, 1, 2, all the way till 3. In total, 1, 2, 3, 4, 5, 6 values.